Hello, welcome to this edition of the Henstitute, in which we are going to look at Chapter 12's thermal expansion and contraction. So the idea is when you actually have a object and you change the temperature of that object, that's a property that's called a thermometric property. And the one that we're going to look at that we kind of use actually for thermometers is this idea of thermal or linear expansion. So if you take a normal solid and it's at a particular temperature here, so this is the original temperature of it, and it has a certain length, if you actually change the temperature of it, that length is going to change. Now, if you increase the temperature, in other words, if your delta T is positive, then you're going to get it to be longer, so it's going to expand. If the delta T happens to be smaller, in other words, it decreases, that's going to be a negative answer, and therefore it's going to shrink. So notice on here that I have the T plus delta T, but delta T could be positive or negative, and so therefore it could change. So this delta L could actually be smaller. In other words, it's contracting. So we're kind of looking at expansion, but realize contraction is going to fall in here as well as we're doing this. The next thing that's kind of neat is this change in length, besides being affected by the temperature. So this last slide is trying to explain that the change in length is going to be affected by your change in temperature. This slide is trying to point out that the change in length is also related to the original length. In other words, let's say I had a piece and I heated it up so it increased in length. So this delta L right here. But let's say I had two of them. Each one of them would increase by that delta L, that different change. Well, then if I put them together, in other words, I had one piece that was twice as long, when it expands, it should expand twice as much. And the reason why I should do that is because each of the individual pieces are expanding by a certain amount. So that change in length is dependent on the original length. If you have something longer, it's actually going to expand more when you change the temperature than if it's shorter, which is kind of a neat kind of concept. What we end up with is what we called our linear thermal expansion equation, and this is the way we're going to write it, that the change in length, so the change in length of the material is equal to the original length, that's what L0 stands for, the change in temperature, and we're going to actually leave this in degrees Celsius, so we're going to be putting everything in degrees Celsius for right now, and then we also need this coefficient of linear expansion. In other words, what is the material? What is being affected? I know that if I heat up aluminum, it's probably going to change length more or differently, I should say, than if I heat up a piece of steel or a piece of titanium or something like that. Also, we know this is going to be different if I'm talking about a liquid versus a solid. So those are going to affect it. And it has a kind of a funny unit. It's the coefficient of linear expansion is just per degree Celsius, or degree Celsius to the -1 power. So that's kind of a weird one. This chart we're going to use a little bit more later, but it has a whole bunch of these linear expansion numbers. So if I was looking up aluminum or gold or something else, I can actually look on that. I'm going to provide that with the notes that we have here. So let's try a problem. I remember having roads that whenever it would get hot, the road would actually push against itself and it would buckle. So it would pop up because those two pieces were pushing against each other so much. And so when they expand, they have nowhere to expand, they just expand up. That's what this one is looking at. So we have these two little concrete slabs. They're originally 3 meters each, and they're doing it out to this many significant figures just so you can see that something does actually change. But they put no space in between them. Most sidewalks, most roads have some kind of space or some kind of material in there to space them. If they didn't, then they're going to cause it to buckle. We're trying to figure out how much it buckles up when this actually happens. So in this particular problem, we're going to actually be looking at that. I'm going to move myself up here just for the time being. And I've got a temperature change here. We're going 25 and 38, so I can find that difference in temperature pretty easily by the delta T. So that's just going to be, 13 degrees Celsius. So nothing too fancy. And then we're going to have to look up concrete. So that's why I gave you this little chart here. Concrete is actually on it, so we've got a value for it. Notice that all the linear expansions are these 10 to the negative sixes. So they're really small numbers. So I take my 12 times 10 to the minus 6, I multiply by the original length, which was 3, and I multiply by the change in temperature. And this is how much one of the concrete slabs is going to change by. It's not changing by that much. So it's pretty small. But what we've got here is, if I imagine that this is buckling, it's kind of creating like a little right triangle here, where the original length was 3 meters, but now the length of this concrete is a little bit more than that, this extra 0.00047 meters. And so I can figure out why by actually using a little bit of Pythagorean theorem here, and I find out that it buckles up by 0.053 meters, or in other words, 5.3 centimeters. So that may not seem like a lot, but that's a couple of inches that it's going to pop up by that. And so that could be important. So just a neat little expansion problem. Bimetallic strips. If you've ever heard of a bimetallic strip, we know that brass and steel are going to expand and contract at different amounts when you change the temperature. And so if you put two of them together, when they heat up, they're going to bend one way because the brass actually expands more for a change in temperature than the steel does. And then when they cool down, it's going to contract more, and so it'll actually bend it. So a use of this is, a lot of things will use what we call a bimetallic switch. So this is like a heating coil inside here. And so the idea is, as electricity flows through here, as it heats up this coil, it's also going to heat up these two different materials. And so if it heats up the brass, it's going to actually cause it to bend away, and that will turn off the switch over here. And so the coffee pot will actually turn off after a certain temperature. And then when it cools back down, it will come back together. And by then it's been turned off, but it's a way to kind of keep it turned off. So bimetallic strips are a kind of a neat method for doing that. Holes. This is kind of a weird one, and I'm going to do a couple of demonstrations next week when you guys get back, so I can actually demonstrate this in person, or I'm going to do some videos of this because there are some great demonstrations of this stuff that I want to make sure I get to you. If I have some material and I heat it up, the hole will actually expand just like it's full of the material. And the easiest way to think of that is, if I broke it up into a whole bunch of little pieces here, then when I heat it, each one of those pieces is bigger. And so when I look at this expanded hole, it should be the same as the piece I took out. So in general, what we're going to say is this little statement right here: a hole in a piece of a solid material expands when heated and contracts when cooled, as if it was filled with that material. So we can calculate this out. Basically, I know that this material is going to expand in all directions, but what that does is it causes basically the hole to expand in all directions as well. And so it's like it's made out of the material, which is kind of neat. I'm going to skip this concept just for right now because I want to jump to this last idea. So it's not just one length that can expand, all of the lengths. So we can actually talk about volume expansion or contraction. And the equation really doesn't change that much. If you notice here, I've got it's just the delta V, whoops, didn't mean to do that, that the change in volume, they just use a beta instead of an alpha, the original volume times the change in temperature, same idea. Now the thing I think is kind of interesting about this, going to go back real quick. If you go back to this chart, I didn't really highlight this much, but if I look at solids, here's the cool part. Their volume is really just the fact that they're expanding three-dimensionally. So the linear expansion in 3 dimensions. Well, check this out. For aluminum, it's 69 times 10 to the minus 6 for its volume, but it's 23 times 10 to the minus 6 for its linear. Well, 3 times 23 is 69. If you've got 14 down here and you multiply by 3, guess what? You get 42. So really the volumes for solids are just 3 times the linear for the most part. The only thing that is important down here is when we're talking about volumes, we've got, when we're talking about a liquid doesn't expand just in one dimension, it's going to expand in all three dimensions. So we have to keep that in mind. And so that's why we give those linear expansion or those volume expansions down there. So let's go back and let's finish with a sample volume problem here. So this volume problem is, if you're familiar in your car, you have a little reservoir for the coolant to actually spill over, because as it goes through the radiator, it's going to get hot. If it's going to get hot, it's therefore going to expand. So what it wants to know, if the radiator is filled with 15 quarts of this fluid, this radiator fluid, and it starts out at 6 degrees Celsius and it increases to 92 degrees Celsius, how much would actually expand or spill into the reservoir? Obviously, they have to tell you the expansion coefficient for that coolant, and we would need to change this 15 quarts into something else, unless you want to leave it in quarts. Here's the cool part about the equation, is the change in volume and the original volume are going to be the same unit. So you could theoretically put them in whatever unit you want if you wanted to solve it that way. So as I do this, we've got this, and that's exactly what we did here. This is coming from the book. They just left it as 15 quarts, and the change in temperature is 86 degrees Celsius. Therefore, the coolant is going to expand by a half a quart, a little over half a quart. Now you have to realize the radiator is also made of material. So we're going to have to look up what it's made out of. And it's probably going to be made out of steel. Nope, this one says a small plastic container. Nope, that's not what we're talking about. And so the radiator itself is going to be made out of steel. So this 51 that they got must have come from right here. Oh, they actually have it as copper, that the radiator was made out of copper. Does it say copper in the problem? I should probably check. The radiator is made out of copper. Yep. So that's where that 51 came from. Sorry, I skipped that. So the radiator itself is going to expand. Now remember, the volume inside, in other words, the hole inside of that radiator is going to expand like it's made out of pure copper. So it's going to expand the same, this 0.066 quarts, and then the difference tells us how many quarts would actually spill over. So there's just some stuff with volume and linear expansions. We'll deal more with this next week as we get into more of our thermodynamics. I hope you enjoyed this edition.